So let's say we're going to explain this again using z-scores. We might say, well, what we could do is if I have let's say I have a whole series of scores on 10 different employees. I've got 3 different sets of scores: work performance, test 1, and test 2. And I want to find out if test performance on 1 is related to work performance, test 2 related to work performance, test 1 compared to test 2. I can do a lot of different relationships. But see how these are on 3 different scales? They have 3 different means, they have different standard deviations. You just glance at this, it's pretty much impossible to see a relationship just by glancing at it. Especially if we got into 50 or 60 or 70 sets of scores, it's kind of worthless. So you could do a scatter plot, and a scatter plot would start to give you a visual, but doesn't give you an exact estimate. But in essence, a scatter plot is asking, are high scores on one variable related to high scores on another? Regardless of the units of measure, right? Doesn't matter the units of measure. I'm now back down to saying high with high, low with low, or vice versa, or somewhere else. In essence, what we've got is a question about z-scores. A z-score gives you how much above, how much below. Are high z-scores on one variable related to high z-scores on another? That's all the question of correlation is really asking. And so the way that we could calculate it the conceptual equation for z-scores says the correlation coefficient is equal to adding the z-score for x times the z-score of y dividing by n minus 1.
The z-score of x times the z-score of y?
Yes. So you remember you have a pair of scores. You turn every score into a z-score, you multiply the z for the first times the z of the second, come up with a third column for zx times zy. You get all those numbers, you add them up, you divide by n minus 1, and you've got r. Now the problem with this, and the only problem with this, is that that's a lot of work. You start getting into 20 or 30 scores, or 40 or 50, there's nothing in your calculator that automatically turns a whole range of scores into z-scores. And so you'd be doing all that by hand, and then multiplying them all, then adding them all. Pain in the rear, right? Okay. So the author says, well, what we could do then, instead, is just use algebra to shift things around. And if we do that, this is the equation we come up with. Sigma xy minus sigma x times sigma y over n, an indication of the covariation, divided by the square root of sigma x squared minus sigma x squared over n times sigma y squared minus sigma y quantity squared over n. But if you look at these numbers, what do we call this number here? This one here, this whole thing. What do we call that? Not the standard deviation, it's the sum of squares for x. What do we call this one?
Sum of squares for y.
Sum of squares for y. And we already know how to calculate this and this, so the only new number here is sigma xy. That's every x score times every y score multiplied by each other, put in a third column, and add it up. Again, time consuming, but rather simple to do mathematically. There's another way to write this exact same formula. And that would be something like this. We could either do sigma xy times sigma x, sigma y over n, all over square root of sigma x squared minus sigma x quantity squared over n times sigma y squared minus sigma y quantity squared over n. But your calculator doesn't give you sum of squares directly. You have to variance square it times n to get your answer. Another thing which is exactly the same this is exactly the same.
So you would
Just use the standard deviations down here, but then you have to divide this by n minus 1.
Is that n minus the number 1 or minus one of the?
N minus 1, it's the number of scores minus 1. So that's just another way to do the exact same thing. Now, generally speaking, sums of squares are always positive because if you take just the x scores and square them, that's positive. Sigma x, which is sum squared, that's positive, etc. But if you have an x and a y, if it's a negative relationship, it means as one's going up, the other's going down. So this will be a big number times a small number, or a small number times a big number. This total is going to could be much smaller than this. So the numerator of this can be negative. This cannot, but this can. So you can see how a correlation coefficient could be negative because of this term right here. The sum of the cross product is the wild card.
So once you get the up top done and you divide it by n minus 1, you divide.
Then you divide that total by
Okay.
standard deviation x times standard deviation y.
And that whole thing was the
Correlation coefficient. Or
Easier?
Or you could just put it in your calculator and have it give you the answer.
Yeah, I'm definitely doing that. Will there be a video on how to do that?
There should be. Hold on, let me,